conference, let's say. Thank you.
Thank you, Marie-Noël. I'm going to read a brief CV of Denis Legrand. Denis Legrand is a volcanoseismologist. He's French. He arrived to UNAM in Mexico City in 2008. He actually got his PhD in France and a postdoc in Japan, Ecuador, and Chile. So he's been working in Mexico during the last 14 years. He got involved into the volcanoseismology of some polygenetic volcanoes, but also of some monogenetic fields in Chile, El Salvador, Nicaragua, and Mexico. He has been through several seismic earthquakes. No one has erupted yet. So let's see what he is going to say about that. In Mexico, he's been studying during the last 4 years what is going on, along with Matthew and several other colleagues, the seismicity in the Michoacán, Guanajuato volcanic field. So, Denis, go ahead.
Okay, thank you, José Luis. So I will speak about seismic swarms. And this work, it's a common work of between seismologists and geologists. So seismologists mainly, we have a short-term, we do short-term description, while geologists are more working on a long-term scale. So we try to combine both time scales, which is not always easy, but it's what we try to do. Some simple questions. Can an old monogenetic volcano be seismically active with seismic activity? So maybe not, but can a future monogenetic volcano be preceded by seismic swarms? Surely yes. So when seismic swarm in a monogenetic volcano field have to be considered with care when we have some of them, no? So let's take an example of seismicity, for example here of Ecuador, but it could be in every other place. So you can see the seismicity related to the subduction, kind of classic tectonic seismicity. But in the crust, you can see that we have some clusters of earthquakes. So we will speak about that. Some of them are swarms and others not. So the outline of my talk, first I will give the definition of a swarm, and I will give you several examples of swarms with tectonic or magmatic in origin, long duration or ephemera swarms, and swarms with small or large magnitude. So the idea of those examples is to show you there is no rule. What I mean by there is no rule, that means that swarm can be very different in opposition with what occurs with earthquake, which have more regular, not a regular, but a systematic behavior. So the definition has been given by a seismologist interested by volcanoes, Mogi, in 1963. And the idea is very simple. It's simply to look at the number of earthquakes in the vertical axis with respect to time. So a main shock, an earthquake of large magnitude, is followed by aftershocks, and the number of aftershocks with respect to time is decreasing exponentially. Sometimes the main shock is preceded by foreshock, but mainly it's the same story. But in some cases, the number of earthquake is increasing and decreasing with respect to time without main shock. So this is what we will call a swarm. And we make the difference between a swarm and a seismic sequence. So as you can see, the definition doesn't say anything about time. That means a swarm can be long or short. It doesn't say anything about magnitude. That means you can have small or large magnitude. And the largest magnitude can occur anytime within the swarm, even at the end of the swarm. So when scientists are asked how long it will last, shall we have a larger magnitude after the beginning of the swarm? The answer is usually, we don't know. When you have a lava earthquake followed by aftershocks, we can say what will occur, but in the case of a swarm, it's not the case. So in the two first examples I show you, this shows that the material is almost homogeneous with an external stress tensor uniform. So this stress tensor is usually the regional stress tensor due to plate tectonics. So we have a big regional and almost homogeneous stress tensor. But when this occurs, usually it produces an extremely heterogeneous medium and with a very concentrated local stress tensor, as we have on volcanoes or geothermal fields, for example. So the definition of the swarm is a cluster of earthquake in space and time without main shock at the beginning of the sequence. But when you have a larger earthquake, it can occur anytime during the swarm. So I will give you here two examples, real examples. To the left, it's a volcanic swarm, and to the right, it's an aftershock sequence. So in the vertical axis, we have the number of events per day. On the horizontal axis, we have time. The case of the volcanic swarm, it's in Aysén in Chile in 2007. And you see that the number of earthquakes increase and decrease, decrease, and so on. So it's rather irregular. And you can see that the largest earthquake occur in the middle of the swarm here or close to the end of the swarm. For a tectonic aftershock sequence, the situation is completely different. We have the main shock. Here it's the case of the Chilean earthquake of 2010, magnitude 8.8, and the number of aftershock is decreasing with time. And in this case, after 1 month or 2 months, the number of aftershocks is almost equal to 0. So this is quite very typical of an earthquake aftershock sequence. There is no big surprise. But in the case of a swarm or volcanic swarms, the story is completely different. In this case, for example, the swarm lasts 6 months. And when you are all the time in the field, it's kind of very difficult because all the time people ask you when it will finish and so on. Can we have a larger magnitude? And as I said, you see, we cannot predict this. And this difference is mainly due to the presence of fluid in the case of volcanic swarms. The fluids make an external stress tensor, and we can have any kind of historical behavior. So quickly, for the case of Chile, we have here the Nazca plate, and which is subducting under the South American plate. The convergence is oblique. So we have a large strike-slip fault here. And in fact, it's not one fault, it's a series of parallel faults. In such a way, you have pull-apart system where most of the volcanoes in South Chile are. And Aysén was inside this pull-apart. It was a fjord. All the seismicity concentrated within the fjord, and you have like 6 monogenetic volcanoes around, which is a little out of scale here, and 2 of them were below the seismicity. And we can show some migration of the seismicity towards the surface. But the magma didn't reach the surface. Another example, it's after the 2004 Sumatra earthquake. Here, it's the surface of the fault, that more 1,000 kilometers, and more or less at the middle of the rupture, we have a swarm in 2005. And you see this swarm was very short. It lasts only 6 days. And within those 6 days, we have 6 magnitude larger than 5.5. So a very, very short swarm in time, but very intensive in magnitude. So completely different of what we have seen before. And below this swarm, this is a high resolution bathymetry. There was also 2 submarine monogenetic volcanoes. I have not the time to describe so much all those cases, but they are interesting. Anyway, this law is known as the Omori law. It's one of the first laws discovered in Japan at the end of the 19th century. And you see it's just the variation of the number of earthquakes with respect to time. And it's decreasing as exponentially with time with an exponent p, which can take those values. No? So here is the few curves for different value of p to have an idea of what's happened. If p is small, 0.8, you can see in this case the sequence of earthquakes lasts more than 1 month. If you take p equal 2, it will last only 15 days. And if p equal to 3, only 5 days. So you can see the interest to know this exponent, because it will tell you how long the aftershocks will last. And this value also can be estimated from the beginning of the sequence, because from the beginning of the sequence, you can already try to fit the curve and have an idea of how long it will last. Unfortunately, this Omori law is not working for swarm. Here it's an example of Chichen volcano in 1982. Before the explosion, we have many earthquakes of similar magnitude and the number of earthquakes respect to time, which is changing all the time. So we cannot calculate the p-value. But this is an information because when you try to calculate p-value and you see the law is not respected, so you can say maybe it's not tectonic. We have another very simple law, which name is the Gutenberg-Richter law that we have seen this morning. So it counts the number of earthquakes greater than a magnitude m. And if you take the log of this number, you have a straight line. And the slope of the line is what we call in seismology B value. We usually use this value B. And for earthquake, usually B is almost equal to 1 or a little smaller than 1. So the meaning of this is, for example, if you have 1 earthquake of magnitude 5, you will have 10 earthquakes of magnitude larger than 4, 100 earthquakes of magnitude larger than 3, and so on. So you see each time we have one magnitude less, we multiply the number by 10 for a b-value equal to 1. So a consequence of this means that you have many small earthquakes and a few large earthquakes. So this is why it is so important to record those small earthquakes. And to be able to record small earthquakes, you need seismometer near the swarm and of good quality. That means a high ratio signal over noise on the records. So this is an example of the Gutenberg-Richter law for the earthquake I showed you before of Chile. And when fluids are involved in the physics of the earthquakes, fluids can be water or it can be magma. This B value is much larger than 1. For example, what we have seen before, it's B equal 1, where we add 100 earthquake larger than 3. If you take B value equal 1.5, you will have only 3, or a little more than 3 earthquake larger than 3. So you can see you have a very big difference between B equal 1 or B equal 1.5 because of the logarithmic law. A wrong idea, sometimes we say that swarms have earthquake of similar magnitude. It is wrong because even for a swarm, the Gutenberg-Richter law is respected. And this wrong idea, I think, comes from the fact that often we don't record all the small earthquakes, but they exist. And so sometimes it makes some confusion. And it is why, again, we need nearby earthquake to record the small earthquake. To do that, and to improve the quality of the station, what we can do is to bury the seismometer. For example, from 1 to 5 meters. And on volcanoes, this is usually easy to do for the soft soil that we have. So to summarize the introduction, you see O'Malley law is respected for tectonic swarm while it is not for volcanic swarm. And the Gutenberg-Richter law is satisfied for both, but with completely different value of B. So this is one very simple way to distinguish a tectonic swarm from a volcanic swarm. So I will show you some results in Michoacán. So you see, in the Michoacán-Guanajuato field, we have many monogenetic volcanoes, and also we have a few polygenetic volcanoes like Tancítaro, which is close to Parícutin. So I guess that we should have many seismic swarms in this region. If you put a station aleatory, I'm quite sure that you will have very small earthquake and very small swarms, because surely there is some motion of magma below this monogenetic field. And around Tancítaro and Paricutin, there was several swarms, we have seen this morning. This is the date of the swarms that occurred. And here we have the Tancítaro volcano, Paricutin volcano here, El Pedregal y Astillero that Patricia Larea spoke on Monday. And we have other monogenetic volcanoes, Janamo, El Metate, El Jabali, and so on. And you see that mostly the last monogenetic volcanoes are aligned along a northeast-southwest direction. But looking at the location of all those swarms, you see that they are more vertical. They are not aligned along this direction. So maybe those swarms are not related to the shallow faults. Here it's a swarm of 1997. We have, unfortunately, few earthquakes for this swarm. I will tell you after why, but they are located here. Tancítaro is here, Paricutin is here, El Pedregal and El Astillero is here, and so on. Janamo here, Uruapan City, and Tancítaro City here. To compare with the 2020 swarm, which is here, after we have the 1999 swarm, also with very few data, and 2006, which is here. And to compare to the 2020 swarm, which is here. So in summarize, here are all the swarms together. This is the color with respect to time. And what we can see, two points. First, and this is horizontal projection, and it is two vertical projection with respect to depth. So we have depths between 0 and 20 kilometers, and between 0 and 20 kilometers here also. So you can see some kind of migration of seismicity from north to south, and kind of migration of seismicity from depth to shallow. And you can see that all the seismicity stops at about 8 kilometer depth. So when we look at that, there is some doubt. Are all those swarms exactly at the same place? Are those spatio-temporal migration real? And why we have this kind of question? Because you see, each time we have a swarm, we go in the field and we install seismic station. We remove the station, another swarm, we go in the field, install seismic station, remove them, and so on. So we never have the seismometer at the same place. So when we want to study a temporal evolution, we have always the doubt if the migration of seismicity is not related to the migration of the seismometers. And because they are never located at the same place. So I insist also to the important to have a permanent seismic station. If really we want to do good job, we need not to move the station at any time because it has a consequence on the quality of the locations of the earthquakes. For example, we couldn't do the Omori law on the Gutenberg-Richter law for the 1997 and 1999 swarms because at that time the records were not continuous. It was automatic triggering of events, and after we store only the events in a memory because at that time there was no large memory. No? So we couldn't record the small earthquake, and as a consequence, we couldn't calculate the Omori law and Gutenberg-Richter law. Even we are not sure that we have all the earthquake because as it is an automatic triggering, we are not sure the job is well done. So again, this example shows the importance to have a continuous record. The deep earthquake between 8 and 15 kilometers below Tancítaro are not aligned, so they are supposed not to be related to a fault. And for the 1997 and 1999 swarm, even if we couldn't calculate the Bay value, we can suspect that this value is high. Why? Because the seismicity is rather diffuse. And a seismicity rather diffuse is related to a high fractal dimension. When you have earthquake everywhere, it will generate a high fractal dimension, and there is a simple relationship between the fractal dimension and B value. So if D is high, B should be high. But you see, it's just a deduction that we do. It's not direct observation, and as you know, it's always better to have direct information. So an interpretation of this is we have some magma ascent, and the earthquake are located between 8 and 15 kilometers between below sea level. And if we see the work on the Auriel Chevrel and collaborators with petrology, they propose that the magma stalls between 5 and 13 kilometers. Here the depth from them have been corrected of the altitude to compare both depths. So what's the meaning of this? So if we have some magma storage, you know we shouldn't have earthquake within the magma. So why we have? Because mainly this magma storage is not a balloon full of magma. No, it's maybe subparallel dike, and maybe you have magma inside the dike, but not earthquake inside the dike. So the magma should be around the dikes. So it's maybe one explanation. Another point is, you see, we have not seismicity in the first 8 kilometers of the crust. But if one time the seismicity will start to be in this range, so we should have some kind of warning, because this should say that the magma is trying to have a path until the surface. And after that, the migration of the magma will accelerate, and it can be very quick. So at that time, we will not have time to buy seismometer and to install them and so on. So we have to do this before. And we don't know very well after what is the path of the magma. It can be from one side and another side, so we don't know exactly where will be the next monogenetic volcano. No? Here it's an example of records in 3 stations. So we have here 3 stations and the 3 components at each station, east, north, and up, and so on for the 3 stations. So you can see in this example a nice P wave and S wave and so on. It's not the best earthquake that I took here. Believe me, there are many are like this. It's not the best one. So not all swarms are volcanic in origin. Here we have experienced last year a swarm close to Los Reyes and Periban that we have spoke this morning. And as this seismicity is rather shallow, 1 or 2 kilometer depth with a B value of about 1, as Mathieu showed this morning, and there is no other manifestation like deformation, magmatic manifestations, and so on. So we think it may have an origin, a tectonic origin. I will show you some earthquake with respect to time. I took the data from the Servicio Sismológico Nacional, and only is shown here the seismicity in Michoacán state. So this is the normal seismicity related to the subduction, and some crustal seismicity. For example, here in Los Reyes, we have in a normal time some earthquakes, but not so much. And this is seismicity in 2022 until just 1 day before the large earthquake of magnitude 7.7 that occurred last year on 19th of September. And here it's seismicity until 25 of September. So we see many aftershocks of this magnitude 7.7. And you see Los Reyes continue as before, so nothing happened. Until the end of September, the same story, and until the 9th of October, so we can see a start of seismicity here, and it continues a little here, and here we are almost one month after the earthquake. So we can see that something happened here. For example, here you see seismicity in a circle, so this is an artifact due to the fact that we have not so much station in Michoacán. In fact, those one have been located with only 1 station. So, and this is the seismicity until the end of the year. So you see we have many earthquakes, and not as much as aftershock of magnitude 7.7, but you see there is quite a large number of earthquakes. And this is a number of earthquakes until the beginning of the year, and few days before. So it's continue. So when will it stop, and why it is so long? So I will tell you next talk. I have few more minutes. Yes. So this is the swarm of Salvador, which is between 5 and 7 kilometers from San Salvador volcano. So I have no time to speak about this swarm. But if we look at the seismicity and we look at the Gutenberg-Richter law and B value and so on, we can see, in fact, it's tectonic in origin. So this is another example where you have a swarm very close to a volcano, but not directly related to the activity of the volcano. You can look at this article if you want to see. So as a conclusion, we have a classical question when we have a swarm close to a volcano: is it tectonic or volcanic in origin? In the case of Tancítaro, we have several swarms at the same place during the last 25 years. So that means we have several attempts of magma to reach the surface, and one day it will. Magma stalls at depths between 8 and 10 kilometers in agreement with petrology. And if seismicity will be shallower than 8 kilometers, so warning, something may happen. No? So it is important to prepare ourselves before the crisis and not during. And we need to study the temporal evolution of seismicity, in particular the depths. And for this, we need to have always the same station in the same place. That means a permanent seismic station. And when we have a seismic swarm near a volcano, in fact, usually it's not completely tectonic or it's not completely volcanic. There is a ratio between both, and mainly because close to a volcano, you have faults. So if you have faults, in one way, they can have an influence on the seismicity. But also you may have magma or hydrothermal activity, and the proportion between both, usually it's what we don't know. So I give you just some clues in this talk to have an idea of this proportion, even if it's not perfect. And the swarm is generated by stress changes, and those stress changes can come from an earthquake or come from fluid migration, or both. So is migration of seismicity directly related to migration of magma, as we saw? Not always. I'm almost finished, no? And a magma reservoir is a network of small, maybe metric dikes. As Mathieu showed you this morning, we can have a very fine image of a dike. And in the case of Tancítaro, you can see that we can have some magma storage below a polygenetic volcano extinct, supposed to be extinct. And this magma can migrate below the polygenetic volcano and generate a monogenetic volcano around this polygenetic volcano. So again, it's why we need nearby seismometer, and I would say about 10 to do better work. No? And also, I show you that small earthquakes are equally important than large earthquakes, especially for swarms, because they occur before the magma exit, and they allow us to have an idea of the image of the dikes, and it allows distinguishing between tectonic and magmatic in origin. Okay, thank you.
Thank you, Denis.
Muchas gracias.
We're not going to take any questions, so I think you'll have enough time at the party to ask him specific questions in order to continue with the program.